And this week we have Dr. Sumit from the Department of Statistics at Columbia University. And his research interests are very broad, including random permutations, mean field models in discrete settings, persistence of Gaussian processes, and graph theory. So today he will tell us something about the mean field approximation in Bayesian regression. So please go ahead, Dr. Mukherjee.
Thanks a lot, Tiandong, for the introduction, and thanks to all of you for joining in. So the talk that I'm going to give today is based on joint work with Sumit, who's currently at Harvard. So before I begin, let me just mention that I'm happy to answer questions during the talk, or I'll try to answer as many questions as I can during the talk. And also I'm happy to take questions at the end. I have like around 40 slides, but I don't need to go through all the slides, but I'll try to answer as many questions. If there are questions, feel free to unmute yourself or put them in the chat. So both are fine with me. So with that being said, let's sort of jump right in. So the talk will roughly have 4 parts. I'll first begin by introducing the problem that we want to study. Then I'll explain the proposed method. It's not a method that we propose. It's a method which has been used a long time for a lot of problems. It's called the naive mean field method, which we'll abbreviate by NMF in this talk. And then I'll explain the rigorous guarantees that we provide for this naive mean field method under some assumptions, of course. And then finally, I will conclude. Okay, so what is the problem that we want to study? So the problem at hand is something that we are very familiar with as statisticians. It's the usual linear regression model, the high dimensional linear regression model. So you have y equals x beta plus epsilon. So y is a vector in Rn. X is your design matrix, which we are going to assume to be non-random. Whatever I say in this talk also applies to random matrix X just by conditioning. And so we will give examples of random design matrices in the talk as well. So we are thinking of settings when n and p are both large. And I'll talk about what type of asymptotics as we go on. So beta is a coefficient vector, which is p-dimensional. And epsilon, is there a question? And epsilon is a vector of IID Gaussians with variance sigma square. And so what we are going to assume is in this talk is that sigma is known. And since sigma is known, there's no harm in assuming sigma equal to 1. Nothing will change if you take a different value of sigma. But we'll also assume that beta is unknown. And beta belongs to, so each coordinate of beta, this should be p, by the way. Sorry for the typo. This should be -1, 1 to the p. So beta, each coordinate of beta lies in a compact interval, right? So it is not important that the set is -1, 1. It could be any compact set on R. That's fine. But our current techniques only allow compact sets, and I'll talk a bit about this assumption as we go forward. But okay, so beta is some compact to the n. So let's just say -1, 1 to the n. Sorry, to the p, not n. Okay, so if you were a Bayesian, what would you do? Well, maybe since you don't know beta, you'd put a prior on beta. So suppose pi is some probability distribution on -1, 1. At this point, we don't have any constraints on pi. So it could be discrete, it could be continuous, it could be anything. But it has to be compactly supported, of course, because like I said, we are assuming that your parameter space is compact to the p. And so we'll assume that the coordinates of beta have a prior, which is IID, following pi. And so then you can write the posterior of beta given y. So I'll denote the posterior by mu, y sub x, because the posterior depends on y and x. And I'll sometimes remove the subscripts y and s just for simplicity of notation. But so the posterior has a density with respect to pi to the p, and this density is just proportional to the likelihood, right? So this is my likelihood, and so this is the posterior, and so okay, we want to study this posterior. So that's a question that we want to study. And why is this hard? I'll try to expand more on this as we go along. But if you expand this out, then you get a quadratic term in beta. So this doesn't actually factorize in beta. So even though the prior was a product prior, the posterior is no longer a product. And this is, common in many examples, including linear regression. But so now, since the posterior is not a product distribution, it has complex dependencies built in. So the question is, what can we say about this posterior? Right? This is sort of at a high level, the question that we want to sort of slowly go into. And so, okay, so what is the proposed solution? This is the naive mean field method. So this is also called naive mean field method based variational approximation. So these are sort of, I'll use these terms interchangeably, even though variational approximation usually applies to a broader class of algorithms, of which naive mean field method is just one. But for this talk, I'll use these two interchangeably. And so in principle, what are we doing? So this is what we are doing. You take this complicated probability distribution mu, and you project it to the set of product measures or product probability measures, right? So you sort of pretend that even though mu has complicated dependencies, maybe there's an approximation of mu under which the coordinates are independent, and maybe this approximation is good enough for some things. It's not going to be good enough for everything, but it's going to be good enough for some things, and we'll try to characterize what this can be used for. And so what is the metric in which you project? Well, we'll use a Kullback-Leibler divergence. And I'll, so of course, it's not a metric, it's not symmetric, it doesn't satisfy the triangle inequality, but still, it has a lot of advantages. In particular, the resulting optimization will become easier, as I will try to explain. But this is the distance in which we'll project mu onto the space of product measures. And so one of the main reasons that people use it is that the resulting optimization that people get is usually easy to compute. And that's sort of one of the main advantages. And and as a result, naive mean field method is computationally very efficient as opposed to MCMC based methods, particularly in high dimensions, right? If P is large, if you want to do an MCMC, things can get complicated. Your distribution can have multiple modes, and you can get stuck in multiple modes. Convergence will take a long time, and proving theoretical guarantees of convergence is, of course, a whole another issue. Naive mean field provides a cheap computation alternative. The question is, okay, what can you prove about rigorous guarantees? But that's sort of, we'll try to answer partially this question. And so what is known? So a lot is known about this high dimensional linear regression model, or the Bayesian version of it. And here we'll just mention some of the papers which are most relevant to our work. And like I said, I mean, we are omitting a lot of references here, and actually there are experts in this virtual room who know about much more about this topic than I do. But I'll here just present a snippet of the known results, which we felt were most closest to what we did. Okay, so to sort of explain what is known, we need to introduce one sort of definition, which will not be important in the later part of the talk, but is important to sort of explain what type of things people have looked at. So one of the things people have looked at is the rate at which the posterior contracts. And so informally, again, there are multiple definitions of this, but I'm just going to take one. So we'll say that the posterior mu contracts at some rate epsilon n. If you look at this random variable, you look at, so you assume that the true model is now a frequentist one, right? But still, you can look at the posterior probability that you take beta from this posterior, and you take beta naught, which is the true beta naught. You look at the L2 norm larger than k epsilon n, and this probability is now a function of y. This goes to 0 under this double limit, right? So roughly it's saying that the error that you commit is of this size, epsilon n. Right, so this is sort of, and again, you can take x beta, and you can look at, you don't have to look at L2 metrics, you can look at other metrics, but this is sort of a generic definition of contraction of the true posterior. And so, okay, so one of the things that people have looked at is the high dimensional sparse setting. So if P is much larger compared to n, and the true beta naught is sparse, then for an appropriate choice of spike and slap prior, so if you choose a prior appropriately, if you have some suitable conditions on X, then your posterior does contract at the minimax optimal rate for this detection problem, right? So what is the minimax optimal rate for the frequent dispersion? Your posterior will contract at that rate, right? So that's sort of already settled. And so this was, first of all, this question has nothing to do with the naive mean field approximation, but in the framework of naive mean field approximation, this follow-up paper shows that the naive, so under similar type of priors and similar type of assumptions, this naive mean field, the approximation mu hat that you get out of this naive mean field procedure also contracts at the same minimax optimal rate, right? So you get sort of a contraction of the posterior and its approximation under sparse settings. And so people have also considered different versions of naive mean field approximations. For example, they work with not the exact likelihood, they work with the tempered likelihood, and sort of that gives you computational advantages, and also you can prove rigorous results about it. And so these type of results have also been studied in the literature. And so all of these results that I'm mentioning here is sort of applies to the setting where X is large. And I'll try to explain what do I mean by X is large. But so what do we expect when X is small? So when X is small, you expect low signal to noise ratios, right? Your signal is low and your noise is high. And and the way we quantify this, or one way we quantify this, is through the operator norm of this matrix X. Remember, X is our design matrix. X is n by p. So the settings that the previous papers looked at, I mean, they sort of were generic, but their results are mostly useful. If I understand correctly, of course, the results are mostly useful when the operator norm of X is going to infinity at rate n, let's say, right? It's sort of blowing up at a suitable rate. Now the sort of the low signal to noise ratio in this talk will be quantified by the operator norm of X is order 1, right? So in this direction, the only result that we know is the work of this paper, who studies the posterior when X has IID Gaussian entries, but then you scale it down so that your operator norm is order 1. It's OP because now X is random. So in this problem, what is known is that if you look at this distance, it doesn't go to 0 anymore. In fact, it converges to a positive constant, which they can characterize using the AMP algorithm, right? So here things are a bit different. Here you don't expect the posterior to contract. So here you don't expect consistent estimates of beta. So in some sense, it's analogous to the Land regime, if I may say so, the Land regime of statistical, like classical statistics. And I'll try to expand more on this towards the end of the talk, depending on the amount of time that I have. But so the Land regime is where you have the contiguous regime, right? Where you don't expect consistent estimates, but where your non-trivial power will go to something between 0 and 1, right? So sort of in some sense, we are claiming that this scaling forces us to be in that regime. And so, okay, so what could be possible questions of interest? Well, what can we do in this low signal to noise ratio, right? What can we do in the setting when X is operator norm of X is like order 1? We will call this the non-contractive regime. We don't use this term formally in the paper, but we explain the term non-contractive regime in the paper. And one comment is that the result that we presented about the non-contractive regime was for IID Gaussian entries. But of course, when you are doing linear regression, you want to be able to handle large class of X. So ideally, you would want to be able to handle deterministic X. Even if you do random X, you want to be handle dependent entries as well. So that's the hope. So we can, the hope is that can we handle both dependent and dependent entries, or deterministic matrices. And another question which is related is that, okay, I talked about this projection, but of course, I mean, it's not clear that there is a unique projection, right? And actually there are examples when the projection may not be unique. And so the question is, when is there a unique projection? When can you do a unique projection of this mean field through this mean field approach? And if there is a unique projection, what does this mu hat tell us about me, right? I mean, can we do something with this mu hat? For example, can we deduce a law of large numbers under the true posterior by studying the corresponding problem under mu hat, right? we can do law of large numbers and CLTs and a lot of things under mu hat, because mu hat is a product distribution. Mu is not. So can we sort of transfer results back and forth? And these are, of course, questions at this point. We'll try to answer some of them, but not all of them in this talk. And finally, and this is also a question which has been looked at, and because this sort of gives you a lot of information about the posterior. So you have this posterior and there's a normalizing constant, which I did not make explicit, but does this normalizing constant converge under a suitable scaling? Usually this convergence tells you a lot about this posterior, right? So in this case, can we say the posterior actually converges in some sense? And again, these questions are purposefully vague at this point. And like I said, we'll try to answer some of these questions in the talk. So this is sort of a rough overview of the problem that we want to study. So we want to study this high dimensional linear regression problem in the non-contractive regime, meaning that upper norm of x order 1, which is supposed to be force us into the contiguous regime where you don't expect posterior contraction. But the question is, what can we say about this model? So that ends the first part of the talk. I'm happy to take any questions if there are any. Okay, so let's sort of move on to the second part, which explains what the naive mean field method is. All right, so we'll try to explain how to do this. Again, this is not something, I mean, this is sort of something which has been done before, but just to explain that this can be done relatively easily, at least for this linear regression problem. So the way to get this mu hat is to minimize the Kullback-Leibler divergence between nu and mu. Mu is the true posterior and nu is a product measure. So this is the space of product measures. So that's the notation for product measures in this talk. So one can easily show that if we are in the non-contractive regime, then this infimum value, it cannot be larger than some constant times p. Right? This constant will depend on this constant, but okay, cannot be larger than the constant times p. And so this is the worst possible value of this infimum. And so we will say the posterior mu is mean field if this infimum value is small of p. Right? You commit asymptotically much smaller error in this approximation than the worst possible error one can commit. So this is our definition for a posterior to mean field. In fact, just as a comment, it doesn't just have to apply to this problem, right? This could be a generic definition, right? I mean, whenever there's a posterior whenever there's any distribution that you have, this could be a definition for it to be mean field, right? I mean, you want this to be small, and you want this to be smaller than the worst case possible. Okay, so throughout this talk, we'll let n and p go to infinity at an arbitrary rate, but in some of the examples, so we'll only put conditions on x. So we'll not assume anything on n and p in our main theorems, but as you will see, when we have to verify those conditions on our design matrices, they will imply some conditions on n and p, which I will make explicit in the examples. But in general, the main theorems apply for any n and p, but there will be conditions on x as I'll show you. Okay, so this, so recall from a few slides back that this is how the posterior looks like. So I'm going to expand the posterior. I can drop the term y prime y because that has nothing to do with beta. So this is the quadratic term which is causing the dependence. This is a linear term. And so I'm going to split the quadratic term into a part which is the off diagonal part and the diagonal part separately. Now, so this is x transpose x is a plus d. And I'll also call x transpose y to be z. So this is a linear term. Now, the reason for doing this is this is also a product. This also splits up. So I can absorb this as part of the base measure. By changing the base measure slightly, I can also absorb this as a part of the base measure. The main difficulty is analyzing this one. So I want to sort of isolate this term, and whatever part I can absorb as part of the base measure, I will. I may or may not absorb this as part of the base measure. It doesn't actually make the math too much different. So I will sort of keep this separate. And so for this talk, we'll assume that all entries of D are constants. We actually don't assume that in the paper, but this just makes a notation simpler here. So therefore, all these terms are sort of D times beta I squared, and you get to absorb that as part of your base measure. So let's do that. So I'm going to define a new base measure, which has a density with respect to the original base measure, but also accounts for this quadratic term, right? Minus half beta squared by 2D, right? So I just put that as part of the base measure. And so if you write your posterior with respect to this new base measure, sorry, there should be a to the power p. It's pi d to the power p. So it's a product here. Then you don't have this term anymore. This term goes into your prior, new prior, so as to say. You just have these two terms left out, right? And so now we want to sort of analyze this. And so let's zyx be the normalizing constant of this thing, right? So d mu is basically this quantity divided by zyx. So that's zyx. Okay, so now we want to do this minimization. We want to minimize the scale distance. So take mu to be an arbitrary product distribution, and let ui be the mean of beta I under nu I. Right? So u is a vector in minus 1 to the p. Right? So u is a vector of means of under nu. And then if you compute this Kullback-Leibler divergence, it's an easy computation, which I'm not going to show, but it's not that hard to do. If you compute this Kullback-Leibler, which is of a product measure with respect to this posterior, this part sort of factorized out. This nu i's are the independent components. Pi d is the changed prior. This is a quadratic form of the vector of means. And you get to do this because the diagonals of A are 0, right? Because A is just the off-diagonal part. So diagonals of A are 0. So you can push the expectation in, so as to say. These are linear terms. You can always push the expectation in. And this is the log normalizing constant. So you have this expression. And now you have to minimize this. So you have to minimize this. Now, suppose I tell you that U is known, right? Suppose I tell you that I do this minimization in 2 steps. First fix U, then do the minimization, and then we'll minimize over U. So if you fix U, this part is a constant, and this part is a constant. This part is always a constant. So this is the only part I need to minimize. So and this part factorizes out. So it's better. So I'm minimizing a one-dimensional probability distribution, the Kullback-Leibler of a one-dimensional probability distribution of this form, and I know the mean. I've constrained the mean. So it's well known that there's a unique minimizer for this problem, which is just an exponential tilt of this base measure pi. So you define the optimal nu has this form. It has a density of this form. You just tilt the base measure pi with respect to theta w, but theta has to be appropriately chosen. It's the same theta. Sorry for the typo again. Theta I should be theta I opt in both cases, right? So there is some theta I opt uniquely characterized, which gives you this optimum. And so here CD is of course the log normalizing constant of this exponential tilt. It can be written explicitly by this integral. So that's your CD here. And so I can characterize the theta I opt in this way. The characterization of theta I opt is that the mean under this measure nu I opt has to be ui. The mean of an exponential family is the derivative of the log partition function. So C prime theta is u. So right, this identifies theta I uniquely. So if I tell you what the vector of means is, then the optimization is sort of immediate, and there's a unique optimizer. And so essentially you have to now do an optimization over vectors, -1, 1 to the p, which is this quantity. And somehow we find it more convenient to take a negative and do a maximization. Again, this should be, the n should be p. Sorry for that. Yeah, this n should be p. So u is always in -1, 1 to the p. So I have to do this maximization problem. There's a quadratic form, there's a linear form, and there's this Kullback-Leibler term. So I have to sort of explain this notation, which I did not do. But this notation is just, this is the exponential tilt of pi d, and this has to have mean ui. This characterizes this exponential tilt uniquely. And that's that. Right? So this is the optimization that I have to do. And so the claim is that this is a much easier problem. It's an optimization over finite, it's an optimization over r to the p or minus 1 to the p, as opposed to optimization over probability measures, which is a much more complicated object. And you can do it in many ways. In many examples, actually, there's a fixed point equation which you can iterate till convergence. We will not discuss these algorithms here, but people have looked at similar algorithms in the literature, where if you iterate a fixed point equation, you get to solutions of this optimization problem if there is a unique optimum. But okay, so we'll sort of explain something along the lines of this as we go forward. But so this is sort of the mean field optimization problem that you get out of this problem, and we'll call this function myx because this depends on y and x. Y plays a role here, x plays a role both here and here. Myx of u. And so if you optimize this, you're supposed to get a good approximation of what of the true posterior, right? So that's what we will do. And so we have reduced optimization to optimization over vectors, which the claim is that it's easier. And as a byproduct, what we get is that log of the normalization constant minus this optimization problem equals this infimum. Right? So this representation comes out for free. And so if mu is mean field, which basically means this q should be u. So this q should be u. There's no q. But if mu is mean field, then what we are saying is this quantity is small o of p. Therefore, this difference is small o of p. And therefore, this equal to this plus small o of p. So we sort of get an approximation for the asymptotic approximation for the log normalizing constant. So this optimization actually tells you what the normalizing constant will behave like for large p. Right? So that's also sort of an immediate consequence of this approach. Any questions that I can answer at this point? So this sort of explains the second part of the talk, and now I'll go over the rigorous guarantees that we provide for this mean field approach.
Sumit, if I may ask, the way you derive this algorithm, haven't seen this version or splitting things up this nicely in other places before. So was this something you did, or you mentioned there was?
We would not like to claim that we did it. I mean, it was written in different versions. I agree with you. We just thought, when we were doing it, we thought this would be a very clean way of presenting.
Yeah.
I haven't seen the exact version, but yeah, when we are doing this, we sort of thought maybe it's better to sort of do the optimization, fixing you, and then doing it over.
To see how this relates to the usual coordinate ascent thing. Maybe there's a relation, but this looks much nicer and cleaner.
Right. So the reason we do this is because we did this first for easing models when beta i's were just plus minus 1. And in that case, of course, there's a direct, whenever you say the mean, you describe the distribution exactly, right? And that's why you directly get this optimization over vectors. And then when we are doing this for general beta, then our thought was that can we view it as an optimization over vectors? Because that's sort of what we saw for the easing case. And so what we did was we said, okay, why don't we fix the means and do it?
Right.
And we didn't sort of see this exact version done anywhere, but I don't want to claim that we were the first ones to do this.
Thank you.
So my guess is that it's done somewhere. We just didn't find it, and so we just did it. Right? That's my guess. Yes. Other questions?
So, Sumit, one quick comment actually. So if you do this maximization iteratively, I think it's probably equivalent to the coordinate ascent, because you're taking expectation in the first step and then you're maximizing over the UIs in the second step. It's probably, I mean, the joint maximization, if you do it iteratively, it's the coordinate ascent, I think.
But if you first do the maximization over U completely and then do the other one, is that also coordinate ascent? Maybe.
Do you get such a nice form then? You don't, right?
So so what we propose is, okay, I mean, what we propose is first do the optimization over U completely, then you get a finite set of optimizers, and then, okay, of course, all of these require assumptions, and then you sort of, as soon as you get the U, the optimizer is unique, right? So as soon as you get the U, you immediately see that the optimizer is this exponential tail.
Right.
Yeah, it is possible that it's equivalent to some version of coordinate ascent.
Okay. Yeah.
So the first result that we provide is sort of a sufficient condition for the mean field approximation to be true, meaning that mu to be mean field. And so again, we are in the contractive regime, but this is the main condition. Actually, this is the only condition, and this is the main condition. I'll try to explain the consequence of this condition. So remember that A is, you take X transpose X, you remove the diagonals, that's your matrix A. Trace of A squared has to be smaller of B. And so under this condition, mu is mean field, and this is an immediate consequence. This is not surprising. This is what we presented in the last slide. But mu is immediately mean field, and so you get more out of this. And so this is why somehow, I guess, this vector representation is something which we like to think about. So if you look at this vector of conditional means, right? So these are everything is under the true posterior here. So even, you don't even need Y to be random here. So Y is fixed and X is fixed, right? So fix Y and fix X, so this means that A is fixed. So if you look at this vector of conditional means, then this vector is an approximate optimizer, right? So this vector is one of the, if this has finitely many optimizers and they are well separated, then this will be one of the close to one of the optimizers. So the exact result is this, under no conditions on how many optimums there are. There could be multiple, by the way. This vector, this is an approximate optimizer. So this optimizer is basically mimicking this conditional vector of conditional means. Again, this is under the true posterior. So finally,
can I ask a question?
Yes, sure.
So,
sure.
Is this also taking into account the misspecified regime as well? Because you said that Y can be treated as a constant. So you do not need the epsilon to be Gaussian, the true data generating epsilon to be Gaussian here. Is it
no, I do need the true data generating. So the truth. So here there is no truth, right? Here Y is just fixed for any fixed Y, exactly, for any Y. It's just, you have this, exactly. You don't need any conditions on Y, but this computation is under the posterior. So you sort of, well, I mean, there's no posterior. This is just, MYX is a function, and this is just this, but you compute this B vector, this expectation I compute under the posterior, given Y and X. So you fix arbitrary Y and X, doesn't have to be from anything. Then you look at this posterior distribution mu YX, which is still a well-defined distribution. Then you compute this vector of conditional means, and then this is satisfied. So Y could be anything, X could be anything, but you have to compute this vector of conditional means under the posterior.
And the probability statement you have is with
under the posterior.
Okay.
So for the first theorem, everything is under the posterior, assuming that, so these are comments which will follow in the following slides, but it's good that you asked this question because all the notations are here. So this is actually, when we say small o of P, this is actually not a probabilistic statement. So Y and X are fixed. So Y and X are a sequence of fixed vectors and matrices here. So this is a non-random quantity, these are non-random quantity, the difference is small o of P. Right? So because Y and X are fixed, the normality constant is just a number.
Makes sense. Yeah, thanks.
But this will change in theorems 2 and 3. For that, we'll need more assumptions. Okay, so theorem 1 continued. So we cannot say, so first of all, we give examples in our paper that there can be multiple optima. In our examples, there are only 2, but I guess we can construct more as well. I'm not sure, but it should be possible. But we can say much more if there's a unique optimizer. So of course, these are sequence here. So I should make precise what do I mean unique optimizer. So suppose there's a vector U star such that any near optimizer, any approximate optimizer of this function is close in L2 sense to this U star. There can be multiple ones, but all of them are close to one particular vector. Then mu behaves, and this behavior will be clear in the next line. So let's just put the next line. Mu behaves in a relatively not too strong way, but not too weak way, depends on the perspective. But mu can be well approximated by a product measure, right? This was the purpose in some sense, right? Why do we do mean field approximations? Well, we do mean field approximations in the hope that we can approximate the true distribution by product measures. Now, if you have multiple, then the intuition at least is, I mean, again, proving this is harder if you have multiple optima. But if you have multiple optima, the intuition is mu is approximated by a mixture of product measures, where the mixture is sort of over the set of optimizers. But then it's very hard to characterize the weights of these mixtures. And if they're uncountably many optimizers, then things are much harder. But if there's a unique optimizer, things are much nicer. Mu is exactly well approximated, which is a very weird statement, but mu is well approximated by a product measure in the following sense. If you take any nice function phi, if you take the linear average of phi, and then if you take this quantity, this is basically the expectation of phi under this product measure, right? I just compute the expectation of phi under this product measure. Then this difference goes to 0 again under the posterior, right? So fix y and x, this difference goes to 0. So we can say much more. So we can say law of large numbers. There will be no CLT. We are not there yet, but we can say something about law of large numbers. If we can show that things are mean field and there is a unique optimizer, right? There is that assumption running around. I mean, there's assumption in part 3, not 1 and 2, but part 3. So far y and x did not be random, but okay, I'll explain when y and x will be random. X will never be random, by the way, but I mean, y will be random at some point. So as sort of rightly asked, this above theorem applies if y and x are random. Not random. If y and x are random, it will continue to hold. You just condition on y and x, and therefore it will also hold if you margin is out. But the way we think about it is just condition on y and x. Your result will continue to hold in probability. And so this assumption, this is the crucial. This assumption, this is not the crucial assumption. Like I said, this is sort of pushes your problem to the non-contractive regime. And so this sort of, you can think of this an extension of the land type settings of classical statistics. I am not sure whether I can go into that. I'll try to sort of go over that a bit, but let's see how much I can cover. So the crucial assumption is trace of a square is smaller of p, right? So this is what gives you the mean field. And actually we show that this is sharp. So there are examples that mu is not mean field if trace of a square is greater than some constant times p. And this also, it's not hard to construct examples. I'll give you one example in this talk. So part 2 gives you a theorem. Part 2 gives you a consideration for this vector of conditional means, which we use to prove this. We use actually part 2 to prove this law of large numbers that you saw in one of the slides. So it basically says that mu is close to the set of optimizers of this main-field prediction formula. So this vector representation actually helps us understand what the optimizer is supposed to tell us. So part 3, of course, develops on this and assumes that there is a unique optimizer, and then we can say more. And so this allows us to study law of large numbers for linear statistics, right, of the form that we mentioned. And so, okay, so one sort of hidden assumption, which is not that much hidden, but I talked about in the early part of the talk, is that beta is compact. Beta lies in a compact space. Now, okay, so we do this for mathematical convenience because the tools that we use are borrowed from these papers and they use compact support. And so we did think about the problem of extend this is non-compact support, and we definitely think it's doable. We do need more assumptions on x here, because here we did not assume lower eigenvalue conditions on x, right? But if you want to integrate over the whole real line, you do need the lower eigenvalue to be of x transpose x to be bounded away, because otherwise you'll not be able to integrate. And you also need some conditions on pi, like maybe finite quadratic exponential moments or the like. So under this, we sort of had a sketch that one could extend this to, So if you're willing to assume more on x, one could extend this to non-compact examples as well. So the proof idea would be just sort of truncating. You sort of compare the original distribution with the truncated one, and you show that the log normally constant ratio It could be large, but it's still e to the smaller of p. But again, this requires work, and this has not been worked out. And this will require you to put more conditions on x, which at that point we did not. So okay, I mean the -1,1 is sort of just an assumption of convenience. You can throw in any compact k as long as your k doesn't depend on n or p, right? It should not change with n or p, right? Then things are fine. So okay, so now let's give examples. Now, contrary to what I said, the examples take x to be random because they are nicer. I mean, in our paper, we also give deterministic examples, but you know. So the first one is not IID. So suppose VIs are a vector of IID Gaussians, but the Gaussians have a covariance built in. You can throw in any covariance that you like as long as its upper term is order 1, and this trace condition is satisfied. You take the off-diagonal part square is small of p. This is our mean field assumption. I'll give you explicit examples later on. So you take the x's to be scale versions of v. This you need to ensure that x also satisfies the upper norm condition. Then x has upper norm order 1. Then we require p to be smaller of n. Right. So this is where the condition. If you want to check this, if you want to check the trace condition, you will see that we need p to be smaller of n. And so if you want explicit examples, so these are 2 examples. I'll also talk about, I don't know how much time I have left. I'll also talk about another example towards the end of the talk. But you can take sigma to be identity plus some constant over p. You can take a block structure. It can be finitely many blocks. You do need to ensure that it's non-negative definite, of course. But other than that, you know, you can sort of play around with the structure as long as this is the only condition you need to keep in mind, right? So you don't need to be identity on the diagonal. It could be other things, right? It doesn't need to be all of them. All of them don't need to be the same. But these are some examples you can play around with. This lambda can be lambda I. So you can play around with these things. So just as a comment, it is known in this that if you take n and p to be proportional, then the mean field approximation doesn't hold. They show that the a and p holds. In this case, the answers don't match. So this result is tight. So you don't expect mean field beyond this condition.
Dr. Mukherjee, you have about 5 minutes left.
Okay, thank you. I'll try to sort of wrap up quickly. So we have another example where B's are IID Bernoullis with the scaling. And if you take X to be suitably scaled, again, if P is smaller of N, then our theorems hold. And in this case, actually, this is not always true, but we actually give a much more general condition for the non-contractive edge in our paper, which applies here, which I'm not going to talk about here. And again, we conjecture this is very strong reason to believe that the mean field does break down if n and p are proportional. So again, this result is supposedly tight. And so, okay, so law of large numbers free of n and p. If you now want a law of large numbers which are free of these n and p, so what we gave was a law of large numbers which depends on n and p because these optimizers depend on n and p. So if you want a law of large numbers free of n and p, then we need to assume more. So then we sort of need to assume that this matrix A converges in some sense and the vector Z converges in some sense. Now we'll assume that the matrices A converges in cut metric, and we'll also assume that Y is generated from a true frequentist model like this, where beta naught is converges to a function. So beta naught is like a nice function interpolated, right? So let me go a bit fast over this part, but I'm happy to take questions on this. So you make a vector into a function. So this is sort of a thing. You make a matrix into a function the usual way. You just blow it up, and again, this is just to illustrate how the function works. And we put the cut metric topology, which is just a usual topology, which again I don't want to expand here because I don't have much time. But the result says, so let me just explain the main result. If you assume that now the true model is coming from this generative distribution, then if you further assume that this matrix P times AP converges in cut metric, and this function W converges in L1, so this basically means this true coefficient vector converges to a function, then the log norm of the constant converges in probability to a constant, which you will see in the next slide. It's horrible, so it's too, so let me sort of quickly explain what this is. All of these functions can be explained in terms of things. X and Z's are IID uniforms and Gaussians. But the main message here is that we can do this, we can get an n-free field limit, and out of this we can get a law of large numbers which is NP free, and this converges is in the following sense. So let me just say this. So this is sort of a question that I anticipate. You take this linear statistic, you take this number, this is a non-random number, you take this difference, you compute the posterior probability of this will converge to 0 in probability as a function of y, where y is coming from the genetic model. So now we assume that y is coming from the genetic model. And so now I'm going to sort of rush saying that this applies to the spike covariance. If you take a spike covariance like this, then our results apply with this function w. You can do finite perturbations. You don't have to do rank 1. You can do general Bernoulli's. It doesn't have to be all the same. Then your answer will be in terms of this this connection probability matrix. Okay, so that's okay. And so if you assume the generative model, we can prove we can prove that the normalizing constant converges. So let's see, and then using this we can prove that this thing converges. We can prove that the number of non-zero entries converges if there is a point mass at 0. So you can handle not true sparse priors, but somewhat sparse priors. So if you have a prior which puts most of its mass at 0, we'll just say the posterior puts most of its mass at 0. One needs defined estimates if you want to say more, and this is work in progress. And the final result is that we also study conditions for uniqueness. Here I give 2 conditions for uniqueness. Either your matrix A has to be in the high temperature regime, or your prior pi has to be nice. And so just to say what nice means, these are some examples of nice. You can have uniform, you can have truncated normals, you can have truncated these, but we need some conditions for uniqueness. It's not true in general. So with that, let me skip the land part entirely, and I'm happy to take questions on this. But let me sort of quickly conclude. So we sort of give a general condition on the design matrix S for the mean field approximation to hold. This result applies to both deterministic and random matrices and allows for dependence. If your data is coming from a true frequentist model, we can show the normalizing constant converges. And in this case, you can get a law of large numbers if your optimization problem has a unique solution. And then we give some sufficient conditions for uniqueness, and it's not true in general. So some problems for future scope. So, can we study the same problem under sparsity where most of the mass is under 0? You will get bounds of size O, small op for free, but then you need bounds of size small os to make meaningful statements, which is work in progress. And the question is, what happens when p is small order proportional to n? We don't expect mean field to be true, but the question is, what is true and what can you say there? We expect the AMP to be true, but again, this is sort of a different problem altogether. And finally, what happens to other problems where people apply the mean field method? What about GLMs, and what about topic modeling? What about any of these posterior distributions? All of these are questions that we plan to study at some point. With that, I would like to end my talk, and I'm sorry for rushing towards that.
Okay, thank you. Thanks, Dr. Mukherjee, for a very nice talk. And I guess we now will have time to take a couple of quick questions, 1 or 2 quick questions. Anybody wants to ask a question, please go ahead.
So Sumit,
yes.
Want to go ahead first? Go ahead.
You can go ahead. Yeah.
Okay, so you use this quantity B, which was the conditional expectation under the posterior of beta I given the other betas.
Yes.
Vaguely recall from the Chatterjee-Dembo paper, they had a similar quantity in their calculations. Is this coming from that? And in a statistical perspective, what is the intuition behind?
So let's see. The first question is, yes, it is sort of borrowing from their framework, but their framework sort of restricted to -1,1 or 0,1, and then of course there was the work of Jun Yan, which extended to compact spaces. So we more rely on Jun's work than Chatterjee-Dembo's, but it is sort of coming from a similar line of attack. So let me give you some intuition. I won't call it a statistical intuition, but sort of what if you want to. So the main proof technique comes out of understanding the normalizing constant, right? So the normalizing constant, you can write it as a sum of this object, like the integral of this quadratic function. Now what they do is, so where is this quadratic function? I think it's in the early part of the slides. But what they do is they say that it's not very costly at the scale at which you are looking. So let's see, where is the, okay. So there should be the posterior somewhere. So if you look at a posterior like this, it is not very costly to replace the vector b by the vector of its conditional means. And it is not very costly to, sorry, beta by the vector of its conditional means. And it is not very costly to replace the vector of this beta also by the vector of its conditional means. So essentially beta prime a beta is very close to b prime a b with high probability. And similarly for this one. So you get to, when you are summing this up, you get to replace this by b's. And then the next step is showing that even though betas can vary a lot, this vector b is sort of much more concentrated, right? Because you expect means to be more concentrated than the original vectors, right? So b's are much more concentrated. And so now you argue that beta could have taken a lot of values, but b takes not too many values. And not too many values means e to this follow of p, not too many values. And now you can sum up, because now if you sum up not too many values, summing is basically a supremum, right? Because the difference between the maximum and the sum is just a factor of the number of terms, which is e to this follow of p, which I just throw under the carpet. So the idea is that you get to replace this beta by its conditional expectation. So it's sort of show a concentration here.
Cool. Thank you.
Sumit, I probably missed some of your remaining slides. So are you having a distributional convergence result for the betas as well at the end of your talk? I mean,
no, so there's no distributional convergence. That's sort of we are. So let me see what we can say about this. So for some specific cases, we can actually do distributional convergence, but for the amount, like for the general setup that we present in this talk, currently we do not know of any distributional convergence results for the betas.
And also you assume that p is smaller of n. Under that setting, probably it's very hard to have some kind of distributional convergence result, right? Because
sorry, continue.
Typically you need like cubic order of p is smaller of n to be able to do that. Yeah.
Right. I suspect that p should be smaller of root n, but again, we haven't proved this. But so so let me say what we know. We actually have proved this in one specific case. If you assume that your x transpose x, after you remove the diagonals, then the remaining matrix is regular, which is a weird assumption for design matrices, right? Why would you assume that? So we actually do that in a different context. If you are coming from the graph theoretic framework, if you have an easing model, so as to say, it doesn't have to be plus minus one, but then a regular graph makes a lot of sense. So if you assume that, so suppose just for now we assume that x transpose x is sort of has regular row sums, then actually we can say a lot more. Then in the regime where p is follow of root n, so our results are in the graph, so I have to translate it carefully. So for regular graphs where d is larger than root n, we have fluctuations for the sum of the betas. But that's a very restrictive setting compared to the generality that I presented here. We are currently working on, so just as a comment, it's much easier to study conditionally centered fluctuation than unconditionally centered fluctuations. So we are in the process of studying that in a wide generality, but that's work in progress. We don't know exactly what the conditions will be in the eventual theorem, but conditionally centered CLTs are much more robust than unconditionally centered ones in these kind of models.
Very interesting. Thank you. Yeah.
Okay, I think, yeah, we're almost running out of time here, but let's thank our speaker again. It's a very nice talk. Dr. Mukherjee, thank you very much for giving this talk. And I guess that's pretty much it for today's talk, and I will see you guys again next week. Bye.
Thank you for having me. Bye.